Hello, I'm glad you're here. Wherever you're listening from, a dark room, a familiar bed, maybe a chair by the window, thank you for making time for this. If things have been busy lately, it's okay. Right now, nothing is expected of you. You're not behind, you don't need to catch up. All you have to do is rest and wonder, just for a little while. This is a space for thinking slowly without pressure, not to solve anything, but to let the questions unfold gently, without needing to close them. Science can feel fast, like a race to answers, but here we're not in a hurry. We're not chasing conclusions, we're letting our minds follow curiosity wherever it wants to go. If you're already finding this moment peaceful, and you'd like more quiet stories like this one, you can leave a like, or subscribe if that feels right to you. And if you're listening from somewhere a little special, maybe a snowy cabin, a city that never sleeps, or your own corner of the world with a well-worn blanket, feel free to share it in the comments. I like imagining the bedtime lights slowly blinking on across the globe, one by one. This video, like always, is meant to be both relaxing and informative. It isn't a replacement for professional help or sleep therapy. It's just a soft place to wonder out loud, a space to stretch your thoughts quietly. Tonight we're going to begin a slow drift into a question that seems simple, but opens up into something much bigger. It's a question about shape, but not the shape of a planet or an object or a galaxy. It's a question about everything. Does the universe itself have a shape? And if it does, what is it? At first, it might seem like the answer should be obvious, or impossible. But as we'll see, the real story is much stranger and more interesting than either of those. To understand the shape of the universe, we'll need to take our time, not to rush toward a final answer, but to feel our way through the ideas one step at a time. We'll begin here with where we are, not floating outside the universe, but inside it, a part of it, and somehow, from here, from this one small point, we're going to try to understand the whole. When you look up at the sky, it feels like you're looking at something flat, a dome, a ceiling, a kind of lid stretched over the earth. That's what it has always looked like. Even ancient people thought so. Before we had telescopes or satellites or models of galaxies, the sky looked like a bowl. Stars rose and set in smooth arcs. The sun followed a curved path. Everything circled overhead like it was fixed on the inside of a shell. That idea stayed around for a long time. Not because people were foolish, but because it matched what they could observe. The sky seemed high, smooth, unreachable. It wasn't empty. It wasn't deep. It was just above. Even now, that impression lingers. When you stand outside and tilt your head back, the stars don't look far away. They feel close enough to touch, arranged on a smooth surface. If you didn't already know better, you might think the universe was a big dome, just as our ancestors imagined. But that impression is misleading. The sky isn't a surface. It's not a lid or a shell. It's the inside of space. It has depth. Every point of light you see is not painted on a backdrop. It's a place, a distance, a history. The stars aren't arranged on a ceiling. They're scattered in all directions, each at a different remove from you, some just dozens of light years away, others tens of thousands. The illusion of a flat sky comes from how our eyes and brains handle distance. We don't have depth perception for objects that far away. There are no shadows, no shifting angles, nothing to help us sense how far a star really is. So we compress the view, we flatten it, and it works well enough for most of daily life. You don't need to know how far away a star is to appreciate how bright it looks. But when we start asking bigger questions, like what shape space has or how the universe is arranged, the illusion becomes a problem. We need to see past it. The first clues came from motion. As telescopes improved, astronomers noticed that stars weren't fixed in place. They drifted slowly over time. More than that, they moved differently depending on their distance. Some were part of groups, others orbited the center of our galaxy. The sky, it turned out, wasn't a surface at all. It was a collection of depths, a set of three-dimensional positions that only seemed flat when viewed from here. Eventually we built ways to measure those distances. One of the earliest methods is called parallax. It's simple in concept. Look at a nearby object from two different positions, and it appears to shift against the background. Hold out your finger and blink one eye, then the other. You'll see the finger jump. Astronomers used Earth's orbit to do something similar. They observed stars 6 months apart from opposite sides of the Sun. The closest stars shifted slightly against the distant background. That shift, measured carefully, revealed their distances. This was a turning point. For the first time, we weren't just seeing brightness. We were seeing depth. We were building a map. The sky began to change in our minds, not from flat to curved, but from two-dimensional to three-dimensional. It wasn't a painting anymore. It was space. As our tools improved, we began to see even deeper. We found galaxies beyond our own. We measured redshift, the stretching of light due to cosmic expansion, and used it to estimate how far away galaxies are. We saw clusters, filaments, voids. The universe turned out to have structure, not neat rows or patterns, but a kind of web. Galaxies are not spread evenly. They collect in strands and walls, shaped by gravity and time. This structure exists in 3 dimensions, across billions of light years. It's not a flat layer. It's more like a sponge, full of gaps and threads, dense in places, empty in others, and we are inside it. Even though we now understand that the sky is a depth map, not a surface, we still talk about it in 2 dimensions. Star charts are flat. Maps of the cosmic microwave background are flat. Images of galaxy distribution are often flattened to fit screens or pages. That's not a mistake, and it's just practical. We live on a planet, we see in 2 directions. We're used to surfaces. But every time we look up, we're not seeing a ceiling. We're looking out through layers of space. We're seeing a kind of cross-section of the past. That shift in perspective, from a flat sky to a volume of space, is essential when we begin asking what shape the universe has. Because once you realize that the stars aren't on a surface, the next question is, what are they in? What is the shape of the space that holds them? Space isn't just a container. It has geometry. It has rules. It can stretch and curve. And that's what we'll begin exploring next. What it means to ask about shape when we're not talking about surfaces or outlines, but the space itself. Not the objects within the universe, but the structure of the universe as a whole. What does it mean to say that space is curved, and how do we measure that without stepping outside of it? We use the word shape all the time, to describe objects, to compare things, to understand how something fits into space, a circle, a square, a sphere, a spiral. These are shapes we can draw, hold, recognize. We learn them early and use them constantly. But when we ask what shape the universe has, the word starts to stretch. It stops being about edges or outlines. It becomes something else. Usually when we think about the shape of something, we imagine we can stand outside it. Look at it from above, rotate it in our hands, trace the boundary. But the universe doesn't offer that option. We can't back away from it and take a photo. We're inside it. Everything we see, everything we measure, everything we are, is part of it. So whatever its shape is, we can only understand it from within. That changes the question. Instead of asking what the universe looks like from outside, we have to ask how it behaves. What kind of geometry space follows? Whether straight lines stay straight? Whether parallel lines ever meet? Whether triangles behave the way we expect? This isn't new. Mathematicians and physicists have been thinking about the geometry of space for centuries. In school, most people learn what's called Euclidean geometry. It's based on a flat, uncurved space. Lines are straight. Angles add up predictably. The surface of a desk, the inside of a box. Those follow Euclidean rules. But there are other geometries too, curved ones. The surface of a sphere doesn't behave like a flat sheet. If you draw a triangle on a ball, the angles add up to more than 180 degrees. If you draw two lines that start parallel near the equator, they slowly move toward each other and eventually meet at the poles. That's not a trick, it's a natural feature of curved space. There's also negative curvature. Think of a saddle. The surface curves upward in one direction and downward in another. Triangles drawn on that surface have angles that add up to less than 180 degrees. Parallel lines spread apart. It's not intuitive at first, but it's just as consistent as flat geometry. It just follows different rules. So when we ask about the shape of the universe, we're really asking which of these geometries space follows on the larger scale. Is the universe like a flat sheet, where the rules of high school geometry work everywhere? Is it like a giant sphere, closed and curved, where space eventually wraps around itself? Or is it like a saddle, expanding forever, curving outward with no loops? Each of those options is more than a metaphor. They come with different predictions. In a closed universe, a positively curved one, if you travelled in a perfectly straight line long enough, you would eventually return to your starting point, like circling a globe. In an open universe, a negatively curved one, space would continue forever, but always with a kind of stretching that affects how light and matter move. In a flat universe, the geometry is uncurved. Space would continue without bending. Parallel lines would stay parallel. But how can we tell which geometry the universe follows if we can't step outside and look at the whole thing? That's where observations come in. We don't need to see the entire universe. We just need to measure how space behaves within the part we can see. One approach is to look at the oldest light we can detect, the cosmic microwave background. It's a kind of snapshot of the universe when it was very young, only a few 100,000 years old. It carries imprints of density fluctuations, like tiny ripples left over from the early stages of expansion. Those ripples have a natural size, a standard scale set by physics. By measuring how large they appear to us, we can tell whether space is curved. Just like a shadow looks different depending on the surface it falls on, those ancient ripples appear slightly bigger or smaller depending on the geometry of the space they travel through. It's a bit like looking at a map of a foreign country and trying to guess what kind of lens was used to take the photo. If the distances look stretched or compressed, you can tell whether the lens was curved or flat. In the same way, the size of these ripples tells us something about the shape of the universe. So far, the measurements suggest that space is very close to flat. Not perfectly exactly flat. We don't have infinite precision, but flat within a narrow margin of error. That doesn't prove it's flat everywhere. It just tells us that, within the limits of what we can observe, space behaves as if it's flat. And here's where the definition of shape gets even more subtle. Because geometry and topology are not the same. Geometry is about local behaviour, how space bends or stretches in a small region. Topology is about global structure, how space is connected overall. It's possible to have a space that is flat in its geometry but still finite in its topology. A bit like a video game world that loops. You can keep walking in one direction forever, not because space goes on endlessly, but because it wraps around. You'd never reach an edge, you'd never fall off. But you wouldn't be in an infinite world either, just a repeating one. That idea challenges a lot of assumptions. When we hear the word infinite, we picture something enormous and unreachable. But a space that loops back on itself could feel infinite from the inside, even if it's technically finite. You could travel forever without running out of room, because you just keep cycling through the same space again and again. So asking about the shape of the universe doesn't always lead to simple answers. It leads to questions about boundaries, repetition, continuity. Are we in a universe that has an edge, or one that wraps around? Are we in a space that's infinite in every direction, or just large enough that it seems that way from our point of view? These questions don't just matter to mathematicians, they affect physics too. The shape of the universe determines how light behaves, how galaxies move, how structures form, and it's connected to the history of the universe, how it began, how it's expanding, and what its long-term future might be. It's tempting to want one final answer: flat, open, or closed. But nature doesn't always work in categories. The universe might be flat overall, but with small fluctuations. It might have a complicated topology that doesn't match any simple model. And since we can only observe a finite region, we might never know for sure. Still, by thinking carefully about what shape really means, not just in pictures but in terms of space and motion, we get closer to understanding what kind of place we live in. Not just where we are, but what kind of space we're in. Not just what objects fill it, but how the space itself behaves. If you were to ask a cosmologist what shape the universe has, you'd probably hear 3 words in response: flat, open, or closed. These aren't just guesses or labels. They describe 3 possible large-scale geometries that space might follow. Each one leads to a different picture of how the universe behaves, and each one carries different implications for what the universe might be like on the larger scales. But before going into what each term means, it helps to pause and ask how we even got to these categories. They come from Einstein's general theory of relativity. That theory doesn't just describe gravity as a force, it describes gravity as the bending of space and time by mass and energy. A planet doesn't orbit the sun because of an invisible pull. It follows a curved path in the geometry shaped by the sun's presence. That curvature on small scales is something we can measure. But Einstein's equations can also be applied to the entire universe. They describe how the universe expands, how it evolved from a hot, dense state, and how the curvature of space can be understood in terms of mass, energy, and pressure. When you solve those equations under the assumption that the universe is the same in all directions and at all locations, an idea called the cosmological principle, 3 basic solutions emerge. Those are the flat, open, and closed models. They're not arbitrary, they come from the math. They represent the only 3 possible types of constant spatial curvature, and each one describes a universe with a distinct shape and behaviour. Start with the flat model. This is the one most people are familiar with, even if they've never thought about it. In a flat universe, space has no curvature on large scales. It doesn't bend inward or outward. Parallel lines stay parallel. Triangles behave the way they do in high school geometry. Their angles add up to exactly 180 degrees. If you shoot a beam of light into the distance, it travels in a straight line forever, unless it hits something. And if the universe is infinite, then it goes on endlessly in every direction. If the universe is finite but flat, then it might wrap around like in some video games or mathematical spaces called toruses. That's the part people often forget. Flat doesn't always mean infinite, it means uncurved. The global shape still depends on topology. Now consider the closed model. This is a universe with positive curvature. The simplest example is a 3-dimensional version of a sphere. Just like the surface of a globe curves in on itself, a closed universe bends space inward. If you travel far enough in one direction, you eventually return to where you started. Not because there's a wall or barrier, but because space loops. Triangles have angles that add up to more than 180 degrees. Parallel lines eventually converge. It's a finite universe with no edges. From inside, it might not feel curved, but its geometry bends everything subtly. Like curves, volumes are smaller than you'd expect. The whole space is self-contained. Then there's the open model, a universe with negative curvature. The shape here is more like a saddle. Space bends outward. Parallel lines diverge. Triangles have angles that add up to less than 180 degrees. This universe doesn't wrap. It expands outward infinitely and keeps curving as it does. Unlike the sphere, there's no looping. Unlike flat space, there's no neutral geometry. It's an infinite space with a very different behaviour. One where the fabric of space stretches away more aggressively as you move through it. Each of these models also describes a different kind of evolution. In the simplest versions of cosmology, without dark energy, a flat universe would expand forever, but just barely, slowing down over time, getting closer and closer to stillness without ever stopping. A closed universe would eventually stop expanding and reverse, collapsing back on itself in a kind of cosmic contraction, sometimes called the Big Crunch. An open universe would keep expanding forever, with the rate of expansion slowing down but never stopping. But those models were developed before dark energy was discovered. Once scientists found that the universe's expansion is accelerating, those connections had to be revised. Now, the long-term fate of the universe isn't just about shape. It also depends on how much dark energy exists, how it behaves, and whether it changes over time. You can have a closed universe that expands forever, or an open one that decelerates depending on the energy content. Still, the geometry matters. It shapes how light travels. It affects how galaxies form. It influences the way gravity collects matter. So cosmologists have spent decades trying to figure out which model describes our universe. They've built instruments to measure curvature, using tools like the cosmic microwave background and large-scale galaxy surveys. And the results so far point toward a flat universe, one where the large-scale geometry is uncurved. The precision of those measurements keeps improving, but the basic result holds. The universe is flat to within a small margin of error. That doesn't mean it's infinite. That's a separate question. It just means that the rules of geometry we know from flat space seem to apply even at the larger scales. Light behaves the way we expect. Triangles obey familiar math. Volumes grow predictably. If the universe wraps around, it does so in a way that doesn't require curvature. It's strange to think about. The universe might be infinite, or it might loop. It might have a weird global topology. But the space we live in, the part we can measure, doesn't curve in or out, at least not in a way we can detect. That could change. Future observations might reveal tiny amounts of curvature, or the flatness might be a kind of balance point, maintained by early cosmic inflation, a period of rapid expansion that smoothed out the geometry. Some theories predict that our flat universe is just one patch of a larger curved space, like a flat tile on a curved floor. Locally flat, globally not. That idea opens new doors. It suggests that even if we measure flatness, we can't be sure of the whole. Our observable region might be deceiving us. The true shape might be larger, stranger, more complex than we can know from here. So while the options of flat, open or closed sound tidy, they're just the beginning. They're categories, frameworks, starting points for thinking. The universe doesn't owe us clean answers. It might blend those categories. It might break them. But by learning what they mean, by seeing how space behaves in each case, we start to build a picture, not just of what space contains, but of what it is. You've probably heard it before. The universe is like the surface of a balloon. It's one of the most common explanations for how space expands, especially in books and documentaries. A balloon inflating, with dots drawn on its surface. The dots move apart as the balloon grows, not because they're crawling across the surface, but because the surface itself is stretching. It's a simple image, easy to remember. But like most metaphors, it only goes so far, and if you hold on to it too tightly, it starts to mislead. Still, the metaphor comes from a good place. It's trying to help you picture something that's hard to picture, space itself growing. Not galaxies flying through empty space like fireworks, but space itself stretching between them. The dots on the balloon represent galaxies. The rubber is space. As the balloon inflates, the distance between the dots increases, even though the dots themselves don't move on their own. They're carried apart by the expansion of the surface. That part is helpful. It shows how expansion doesn't need a central point. Every dot sees the others receding. No one is in the middle. From the perspective of any given point, the others are moving away. That matches what we observe. Galaxies are moving away from us and from each other, with the more distant ones receding faster. That's what you'd expect if space itself is expanding uniformly in all directions. But problems come when the metaphor is taken too literally, because in real life, a balloon expands into something. You blow air into it. It gets bigger in the surrounding room. You can look at the balloon from outside. You can see its entire shape, hold it in your hands, watch its surface curve. That's where the analogy breaks down. The universe isn't a balloon floating in a larger space. There's no outside it's expanding into. There's no container, no air being added. The universe is everything. It's not growing into anything else. It's just growing. And that's where the metaphor starts to cause confusion. People often ask if the universe is expanding, what is it expanding into? The balloon image makes it feel like there has to be a surrounding space, something that holds it. But there isn't. The expansion of the universe means that the distances between unbound objects, like galaxies not held together by gravity, are increasing over time. The space between them stretches. The size of the observable universe increases, but not because we're pushing into some outer region. There is no outer region. Another way the metaphor misleads is by representing the universe as two-dimensional. On a balloon, the dots lie on the surface. The surface is two-dimensional. It has length and width, but not depth. The balloon itself is three-dimensional, but the third dimension is outside the surface. In the metaphor, the idea is that we're like creatures living on that surface unaware of the third dimension. That can help people understand how space can curve without having an edge. But it also introduces problems, because our universe isn't two-dimensional, it's three-dimensional. The surface of our universe isn't a flat sheet, it's a volume. So if you want to use the balloon as a model, you have to imagine a three-dimensional analogy of a two-dimensional surface, and that quickly becomes hard to visualize. There are also questions the balloon can't answer, like what happens in the center? What's the shape of the whole thing? Can you draw a straight line forever? In the balloon model, the surface has no center. The inside of the balloon is not part of the surface, so the expansion has no middle. But in real life, people often ask whether the Big Bang happened at a specific location, a point in space. The answer is no. The Big Bang didn't happen at one spot. It happened everywhere. Every point in space was once closer together. The expansion isn't from a center outward. It's from all points at once. That's another place where the balloon image helps, just a little. From the surface, there is no central point. Every dot sees the others moving away. Every dot is part of the expansion, and that reflects what we observe in the real universe. No matter where we look from, Earth, a different galaxy, even a hypothetical alien world, we see galaxies receding. That tells us the expansion is uniform, not centered. But again, the danger is taking the metaphor too far, because unlike a balloon, the universe doesn't have a skin or a boundary. There's no edge you can reach. If you kept travelling in a straight line, you wouldn't hit a wall. Depending on the shape of the universe, you might circle back to where you started, or you might go on forever. But either way, there's no surface you can poke through, no layer you can peel back, just more space. So the balloon is useful, up to a point. It shows how expansion works without requiring movement through space. It shows how space can stretch without things flying through it. But beyond that, it starts to blur the truth. The real universe is not sitting in someone's hand. It doesn't have a center. It doesn't push into anything else. It's not a skin stretched over something larger. To really understand what's happening, you have to shift your perspective. Stop imagining objects moving inside a space. Start imagining space itself changing. Galaxies aren't flying through a room, the room is growing. Not into a bigger room, not into emptiness, just stretching. More distance between the same objects, more space between points. That's expansion. It can feel unsatisfying. The mind wants something more solid, a visual, a shape, a frame, something to put the universe in. But the universe isn't in anything. It's the frame itself, and understanding that takes letting go of a lot of everyday thinking. That's why even scientists use metaphors like the balloon, not because they're perfect, but because they offer a step toward the truth. a way to shift the mental model just enough to make room for new ideas, and then, once they've done that job, the metaphors can be set aside. So while the universe isn't a balloon and space isn't a rubber sheet, those images can still help open the door, as long as we're careful not to stop there. When people first hear that the universe is expanding, the next question is almost always the same. Expanding into what? And once that settles, another question follows quickly behind it. Does it have an edge? Could you travel far enough to reach the end of the universe? Is there a boundary out there, some invisible wall where space just stops? These are natural questions. They come from everyday experience. Everything we know has a boundary. Cities have limits. Maps have borders. Even the planet has a surface you can walk across and measure. We're used to things being inside other things. A room is in a house is in a neighborhood. Everything seems to sit within something else. So when we hear that the universe is a space, we instinctively want to know where the space ends. But the universe doesn't work that way. Space isn't inside anything. It's not sitting in a larger container. It's not expanding into emptiness. It's not growing toward a destination. It's not unfolding across a floor. Space is the thing. It's the frame itself. And as far as we can tell, it doesn't have a boundary. That can be hard to accept. We want a mental picture, an edge to touch, a wall to lean against, a sign that says, this is the farthest point. But if the universe is infinite, then there is no edge. And if it's finite but curved, like the surface of a sphere in 3 dimensions, it still doesn't have an edge, just a looping structure. You could travel forever and never fall off. You'd never hit a wall. You just keep moving through the same space. In both cases, the result is the same. No boundary, just more space in every direction. Still, it's worth thinking about why this is so hard to picture. We're used to finite objects, even a globe, which doesn't have a boundary, is something we can see from the outside. But we can't see the universe from the outside. There is no outside. There's no higher dimensional place we can back into and take a look at the whole thing. We're not standing apart from it. We're inside it, looking around. That's what makes it different. The surface of a sphere in 2 dimensions is a good analogy, because from the perspective of a 2-dimensional creature living on the surface, the space is finite, unbounded and curved. There's no edge they could reach, no cliff to fall off, just a surface that loops. But unlike a balloon, our universe doesn't have a surrounding space. It isn't embedded in a higher dimensional world. The curvature, if it exists, is intrinsic. It comes from the properties of space itself, not from how it sits in something else. So when people ask where the edge is, the answer is there isn't one. Not in any direction, not on any scale we can detect. Space just continues, either infinitely or in a way that wraps back on itself. The idea of an end gets even more complicated when you bring time into the picture. Because people also ask, did the universe begin at a point in space, and will it end in one? But the Big Bang wasn't an explosion in a location. It wasn't something that happened somewhere. It was something that happened everywhere. All of space was once much denser and hotter. All of space began to expand, and that expansion continues. There wasn't a center. There wasn't a starting point in space. There was a moment in time, the beginning of the observable universe as we know it, but not a location you could point to. And the same goes for the idea of an end. If the universe is infinite, then it will keep expanding, not toward a boundary, but within itself. And if it's finite and looping, it will do the same, grow without ever needing an edge. So end becomes a question about time, not space. Will the expansion continue forever? Will galaxies drift so far apart that light can no longer travel between them? Will stars burn out, black holes evaporate, and the universe settle into cold stillness? Those are real questions, but they're not about boundaries in space. They're about what happens to matter, energy, and time. One of the most interesting ideas in physics is that you can have something finite without it needing to be bounded. A loop, a closed surface, a structure that is complete and continuous but with no edge. That's not a trick. It's a feature of certain geometries. The surface of a sphere has no boundary, but it encloses a finite area. A torus, a donut shape, can do the same. These shapes don't need outer edges. Their structure is defined by how they connect within themselves. Some models of the universe borrow these ideas. They suggest that space may be finite but unbounded, closed in on itself, looping through higher dimensions we can't access directly. These aren't science fiction fantasies. They're mathematical possibilities supported by general relativity. They're just very difficult to confirm with observation. So far, we haven't seen any evidence of a boundary. No edge to space, no limit we're approaching. And every observation we've made suggests the same thing. Wherever you go in the universe, it keeps going. The distribution of galaxies looks the same in all directions. The cosmic microwave background doesn't show a preferred axis. There's no sign of a wall, a border, or a cutoff. That doesn't prove the universe is infinite. But it strongly suggests that if there is a limit, it's much farther away than anything we can observe, or it's a kind of limit that doesn't show up as an edge, a limiting curvature, a topological closure, something subtle, not abrupt. This is why cosmologists often shift the conversation away from boundaries and toward geometry, because asking about edges implies a kind of spatial outer layer, and that's not how the universe appears to behave. It's more accurate to ask what the structure of space is, how it's curved, how it's connected, whether it loops, whether it stretches endlessly. Those are questions we can approach through observation and theory. So when people imagine reaching the end of the universe, flying outward, leaving galaxies behind, heading into darkness, the real answer is quieter. There's no barrier waiting, no final line. You just keep going, through more space, more time, more of the same structure, unless the shape brings you home. And if that's true, if there are no edges, and maybe no end, then what we're really trying to understand is not what's outside the universe, but what's inside it, and how that inside is built. What kind of space we're moving through, how it curves, what it connects to. Infinity is a word we hear often. It comes up in math class, in science fiction, in conversations that drift late into the night. It's easy to say, but hard to hold on to. Not because it's too abstract, but because it refuses to end, and our minds aren't built for that. We like things to be countable, defined. If you walk across a room, you can measure the distance. If you stack blocks, you can keep track of how many. Even very large numbers we can still imagine as groups. Millions, billions, trillions. They might feel big, but they still have boundaries. They end. Infinity doesn't. It isn't just more than we can count. It's more than can be counted. Not just a number we haven't reached yet, a concept that doesn't stop. So when cosmologists say the universe might be infinite, they're saying something enormous. Not just big, not just vast, infinite. A space that continues in all directions without limit. No edge, no boundary, no total. Just more space. But what does that actually mean? If you were to set out in one direction and just keep going, would there ever be a time when you stop? In an infinite universe, no. You'd never reach a wall. You'd never come back around. You just keep moving through new regions of space, new galaxies, new stars. Forever. That's the idea. But it's not something we can test directly. Our observable universe is finite. There's a horizon, the farthest light we can see, and beyond that, the light hasn't had time to reach us. So when we talk about an infinite universe, we're talking about what lies beyond that horizon. Not something we've measured, but something we infer. The cosmic microwave background shows us a snapshot of the early universe. From the patterns we see and the way those patterns behave, we can estimate the geometry of space. And those measurements, from satellites like WMAP and Planck, suggest that the universe is very close to flat. Within the margin of error, that points toward infinite. But the margin still exists. We can't rule out a small amount of curvature. We can't prove the universe is infinite, but it might be. Infinity raises all kinds of strange possibilities. For one, it suggests that the amount of matter and energy in the universe could be infinite too. If space never ends, and galaxies continue in all directions, then there are infinitely many stars, infinitely many planets, infinitely many regions just like ours, and, in some versions of cosmology, maybe even regions identical to ours. That's where things start to feel less scientific and more philosophical. Because if the universe is infinite, and the laws of physics are the same everywhere, then every possible configuration of matter could eventually appear just by chance. That's the basis of some ideas about cosmic duplication. Somewhere far beyond our horizon could be a region that looks exactly like Earth, with a solar system like ours, a version of you thinking about the same question on the same kind of night. Of course, that's not a scientific claim. It's a consequence of how infinity behaves in certain models. You don't need to believe in copies of Earth to take the idea of an infinite universe seriously. You just need to accept that space might go on, not for a long way, but forever. That also changes how we think about the Big Bang. People sometimes imagine the universe starting as a single point, a kind of seed that exploded outward. But if the universe is infinite now, it was infinite then too, just hotter, denser, and more compressed. The expansion didn't stretch a point into infinity. It stretched an already infinite space into a cooler, wider version of itself. No center, no edge, just infinite space changing with time. Infinity also complicates the idea of fate. In a finite universe, you can talk about totals, how much matter there is, how long things will last, what comes after the end. In an infinite one, those totals break down. You can't compare one infinity to another without special rules. Probabilities stop working the way we expect. Predictions become trickier, because the scale is too large. There's no complete picture, only what we can see and what we can model. And there's the psychological side too. The feeling of trying to imagine an infinite space can be overwhelming. The idea that you could travel forever and never arrive at the edge, that galaxies continue beyond every galaxy you see, that whatever distance you imagine, there's always more beyond it. It can feel exciting, or uncomfortable, or strangely peaceful, depending on how you think about it. Some people find comfort in the idea that there's no outer wall, that space just continues. Others find it disorienting, but either way, infinity reminds us that the universe isn't shaped for human intuition. It doesn't stop when we want it to. It doesn't wrap neatly into a box. It just is. However large or endless that turns out to be, still, we can ask meaningful questions. Even in an infinite universe, local rules still apply. Physics still works. Galaxies still form. Stars still shine. We can study those patterns, map the structures, and use what we see to make sense of what we can't. Infinity isn't a goal, it's a condition, a way space might behave. And if the universe is infinite, then every part of it is just a small piece, even the piece we call home. Light feels fast, it feels instant. You flip a switch, and the room is bright. A spark flashes across a sky. A reflection appears in a mirror. But what's easy to forget is that light always takes time to travel. It has a speed, the fastest speed in the universe, but still a speed. And because of that, it doesn't just move through space. It traces the shape of space as it goes. That's why light is so valuable to cosmologists. It's not just something we see, it's something that carries information. It remembers. A beam of light travelling from a distant galaxy carries a history of everything it's passed through. Every curve in space, every gravitational pull, every stretch of distance. The path of light is shaped by the shape of space itself. This is where general relativity comes in. Einstein's theory describes how mass and energy bend the geometry of space. And light, even though it has no mass, still follows that curvature. It moves along what's called a geodesic, the straightest possible path in curved space. But when space is curved, a geodesic isn't always what we would call straight. It can bend, twist, even circle back. This is most obvious near massive objects. When light passes close to a star or a galaxy cluster, its path bends slightly. That's called gravitational lensing. The object doesn't emit the light, it just distorts the light that passes by. We've observed this many times. Light from distant galaxies bends around foreground galaxies, creating arcs, rings, and duplicate images. It's a real effect, not an illusion. Space itself is bent by mass, and light follows that bend. Gravitational lensing is one of the tools scientists use to study the universe. By measuring how light is bent, they can infer the presence of mass, even mass they can't see directly. That includes dark matter, which doesn't emit or absorb light, but still has gravity. Light passing through a region of space with dark matter will curve slightly, revealing that something is there. But gravitational lensing does more than map mass. It also hints at the shape of space on larger scales. If space were curved globally, not just around individual objects but across entire regions, then light travelling through those regions would follow that curvature. It would change direction subtly over billions of years. That change would affect how we see distant galaxies, how the cosmic microwave background looks, how the structure of space appears. In a flat universe, light travels in straight lines. Parallel beams stay parallel. Triangles formed by light paths behave exactly the way Euclidean geometry predicts. But in a closed universe, with positive curvature, light paths converge. Lines that start parallel slowly bend toward each other. In an open universe, with negative curvature, the opposite happens. Light paths spread apart, triangles stretch, volumes behave differently, so by measuring how light moves and how it spreads out over time, we get clues about the underlying geometry of the universe. The cosmic microwave background is especially useful here. It's not just a faint glow, it's a precise map of ancient light. It shows us how space was shaped 13.8 billion years ago. And from that, we can infer the curvature of space, because light preserves the geometry it travels through. Another way light reveals space is through redshift. As the universe expands, the space between galaxies stretches, and as light travels through that space, its wavelength stretches too. It shifts toward the red end of the spectrum. That redshift tells us how far light has travelled, not just in distance, but in time. It's a kind of cosmic timestamp. But redshift also interacts with curvature. In a curved universe, distances behave differently. The relationship between redshift and distance depends on the shape of space. That means by measuring both, how far away a galaxy appears and how much its light is redshifted, scientists can test different models of cosmic geometry. It's like tracing the route of a car by listening to how the sound of its engine changes as it passes. The sound tells you something about the path, the motion, the speed. In the same way, the light from distant objects tells us about the road it travelled, and that road is the structure of space. Even more subtly, light can be distorted by the expansion of space itself. As the universe grows, photons, the particles of light, lose energy, not because they're passing through something, but because the space they're travelling through is stretching. That changes how we see the light. It alters its temperature, its colour, its intensity. All of that carries clues. None of these effects are dramatic on their own. They're quiet, cumulative, spread across billions of light years. But taken together, they paint a picture of the universe's geometry, drawn not with rulers, but with beams of light. And what they show is a space that behaves, on average, very much like flat space. Not perfectly, the measurements aren't infinitely precise, but close enough that the rules of Euclidean geometry seem to hold. Light doesn't bend across empty space in unexpected ways. The patterns in the microwave background don't show strong curvature. The large-scale structure doesn't warp wildly. Still, light's journey is never completely straight. Even in a flat universe, gravity bends it. Expansion stretches it. And over long enough distances, even the smallest effects add up. That's why every beam of light from a distant galaxy is more than just a line. It's a record, a message, a quiet signature of the shape it travelled through. So when we ask about the shape of the universe, we're not just asking about space. We're asking about how light moves, how it carries memory, how it reacts to curves and mass and motion. And if we follow those light paths carefully, we begin to see something else, the early moments of the universe. Not just how light travels now, but how it first began. What the shape of space was when light first started moving freely, and what that tells us about how space itself came into being. There's a glow that fills the universe. You can't see it with your eyes, but it's there. It comes from every direction. It isn't tied to stars or galaxies. It doesn't flicker or fade. It's been here longer than anything else we've ever observed, and it holds the memory of a time when the universe was completely different. This glow is called the cosmic microwave background, sometimes just the CMB. It's the oldest light we can detect, and one of the most important tools in cosmology. It isn't bright. In fact, it's incredibly faint, but it's everywhere. It surrounds us, and inside it are patterns, tiny fluctuations, that whisper clues about the shape and structure of everything that came after. To understand what it is, you have to go back to the early universe. About 13.8 billion years ago, everything was hot, dense, and packed together. There were no stars yet, no galaxies, just a thick soup of particles, photons, and energy. In those early moments, light couldn't travel freely. It was constantly bouncing off charged particles, electrons and protons, unable to move more than the smallest distance without interacting. The universe was opaque, like the inside of a cloud. But as the universe expanded, it cooled. And eventually it reached a point where electrons and protons could combine to form neutral atoms. That changed everything. With fewer charged particles around, photons no longer scattered constantly. They could travel freely for the first time. That moment is called recombination, and it marks the origin of the cosmic microwave background. The light released at that moment has been travelling ever since, for billions of years, stretching with the universe, cooling as it goes. What was once brilliant and hot is now cold and faint, not gone, just redshifted, shifted from visible light down into microwave radiation, but still present. And that's what we detect today, a faint, nearly uniform glow coming from every direction in the sky. It's the light from the moment the universe became transparent, frozen in time and stretched across space, a kind of photograph of the infant cosmos. At first glance, the CMB looks smooth, almost perfectly even, but when scientists started measuring it closely, they found small variations, tiny differences in temperature, only a few millionths of a degree. Those small fluctuations are crucial. They represent regions where matter was slightly denser or thinner than average. Over time, those slight imbalances grew into galaxies, stars, and the large-scale structure of the universe. But those patterns don't just tell us about what came next. They also tell us about the shape of space itself, because the light from the CMB has been travelling for billions of years across enormous distances, and the way it looks now depends on the geometry it passed through. If the universe were closed, like a three-dimensional sphere, that would affect how the patterns in the CMB appear. The size of the fluctuations would look slightly different. If the universe were open, with negative curvature, the patterns would appear smaller, stretched across a saddle-shaped space, and in a flat universe the patterns would retain their original scale, more or less. By measuring those patterns precisely, cosmologists can test which geometry best matches the data. And what they've found is remarkable. The CMB patterns fit best with a flat universe. Not curved inward, not stretched outward. Flat. At least flat within the precision of our instruments. It's not a perfect measurement, no observation is. But it's close enough that flatness is now the default assumption in most cosmological models. And that flatness tells us something deep. It tells us that the large-scale structure of space, across billions of light years, behaves according to the rules of Euclidean geometry, at least as far as we can tell. That doesn't mean the universe is flat everywhere. It means the part we can observe is flat to within a very small margin of error. There could be curvature we can't detect, either because it's too small to notice, or because it lies beyond our observable horizon. But for now, the CMB tells us that space, as far as light has shown us, follows flat rules. This CMB also tells us about the contents of the universe. The size and distribution of the fluctuations depend on how much matter exists, how much dark matter is present, how much radiation there was, and how quickly the universe was expanding. By fitting models to the data, scientists can infer those values. That's how we know that ordinary matter, the kind that makes up stars and planets, is only about 5% of the total. Dark matter and dark energy make up the rest. So in that faint glow, we find answers to several questions at once: the age of the universe, the composition of its contents, and the geometry of space, all from a pattern of tiny temperature differences frozen into light that's been travelling since before galaxies formed. There's something almost quiet about that. The idea that the most ancient light still lingers around us, barely visible but rich with information. Not loud, not dramatic, just steady, still making its way to us, one photon at a time. The instruments that detect the CMB, like the COBE, WMAP and Planck satellites, are built to see what we can't. They tune into wavelengths that our eyes miss. And the maps they produce are not photographs in the usual sense. They're portraits of density, motion and shape. A fingerprint left by the early universe still intact. From those fingerprints we build our models, we test our assumptions, and we trace the outlines of a space we can't leave. The CMB doesn't just show us where we came from, it shows us what space has done since then, how it's expanded, how it's behaved, and what kind of shape it has taken. When most people hear the word curved, they picture something bending in space, a road that turns, a ribbon twisting in the wind, a ball, a hill, a cup. Curved things are shapes with edges that bend or fold. But when cosmologists talk about curved space, they mean something very different. It's not space curving inside something else. It's space itself that has curvature. And it doesn't need a higher dimension to do it. This is one of the hardest ideas in cosmology, not because it's abstract, but because it pushes against the way we usually think. We're used to shapes being defined by their outlines. A sphere curves because we can see it bulging outward. A saddle curves because it dips and rises. But that kind of curvature, the kind we picture, depends on having an outside view. You look at a ball from the outside and say, that's curved. But with space, we're not outside. We're in it. So curvature has to be defined from within. That's exactly what general relativity does. It describes curvature not by how something looks, but by how distances behave. If you're standing in curved space, you can detect that curvature by how objects move, how light bends, and how shapes behave over large distances, without needing to step outside and look. One way to picture it is with triangles. In flat space, a triangle's angles always add up to exactly 180 degrees, but in curved space, that rule changes. On a sphere, a surface with positive curvature, you can draw a triangle whose angles add up to more than 180. Imagine drawing one from the North Pole down to the equator, over to another point on the equator, then back up. The triangle looks strange, but the angles are bigger. That's a sign of positive curvature. On a saddle-shaped surface, one with negative curvature, the angles of a triangle add up to less than 180. The surface curves away in two directions. Straight lines diverge. That's a sign of negative curvature. The key point is that these differences can be measured without leaving the surface. You don't need to step into a third dimension to find the curvature. You just measure how distances behave inside the space. Now imagine doing the same thing in three-dimensional space. You can't see the curvature, but you can still measure it. You fire beams of light in different directions. You watch how they move. You build geometric shapes out of those beams, and by measuring how the shapes behave, whether the angles add up the way they should, whether lines converge or spread, you can tell whether the space is curved. That's what scientists do when they study the large-scale geometry of the universe. They don't step outside space. They look at how light moves, how galaxies are distributed, and how the ancient patterns in the cosmic microwave background appear. They look for signs of curvature in the way space behaves from within. This curvature isn't local, like the curve around a planet or a black hole. It's global. It stretches across the universe. It doesn't come from a single source of mass. It comes from the way space is built, and it can be positive, negative, or zero. If the universe has positive curvature, space bends inward. It's like the three-dimensional version of a sphere. If you travel far enough in one direction, you might come back to where you started. You'd never hit a wall. There'd be no edge, just a closed loop in space itself. If the universe has negative curvature, space bends outward. Lines that start parallel slowly drift apart. Volumes expand faster than you'd expect. And if you tried to make a large triangle with light beams, its angles would add up to less than 180. This kind of space is infinite, open, and expanding in all directions, a kind of cosmic saddle. If space has zero curvature, it's flat. Not flat like a table, but flat in the mathematical sense. Distances behave the way Euclidean geometry predicts. Parallel lines stay parallel. Triangles follow the usual rules. Light moves in straight paths unless bent by gravity. And the universe can be infinite or finite depending on how it's connected. The shape of space isn't about whether the universe looks like a ball or a tube or a sheet. It's about how space behaves internally. That's what curvature really means. And this is where people sometimes get confused by language. We hear that the universe might be curved and imagine it must be curving into something, like a ball curves into space. But curved space doesn't require a surrounding space to bend into. That's an external way of thinking. The kind of curvature we're talking about is intrinsic. It can be measured by observers inside the space, just by looking at how lines behave and how shapes hold together. This idea isn't just theoretical. It has real consequences. It affects how light travels across cosmic distances. It changes how gravity works on the larger scales. It influences how the universe evolved and how it might continue. The curvature of space even plays a role in time. In general relativity, space and time are woven together into what's called space-time. When space is curved, time is too, and the curvature of space-time tells matter how to move. That's what gravity really is. Not a pull, but a response to curved geometry. So when we say space might be curved, we're saying that the stage on which everything happens, the structure that holds stars, galaxies, and light itself, might have a shape we can't see from the outside but can measure from within. And the more we measure, the more that shape becomes clear, or at least partially clear. We're not guessing. We're building models, making predictions, testing ideas, using light as a tool, using geometry as a guide. If the universe really does have a shape, a large-scale geometry, then it matters what kind. Because each shape isn't just a label. It's a set of rules, a structure, a way for space to behave. And even though we can't float above the universe and look down on it, we can use these shapes, sphere, saddle, flat sheet, to understand what kind of space we might be living in. Start with the closed universe. This is the one shaped like a three-dimensional version of a sphere. That doesn't mean it looks like a ball. It means space curves inward. The geometry is positive. Parallel lines slowly come together. Triangles have angles that add up to more than 180 degrees. If you could travel far enough in one direction without hitting anything, you might eventually return to where you started. There's no edge, but also no infinite stretch. It's a finite universe, without boundaries. In this kind of universe, volume grows more slowly than it does in flat space. Light paths curve gently inward. The total amount of space is limited, but not in the way a room is limited. There's no wall, just a loop. And that loop exists in 3 dimensions, not along a surface. So you wouldn't feel like you were turning. You wouldn't notice a bend. But over vast distances, you'd find that the geometry wraps around. Now take the open universe. This one curves outward. It's shaped like a 3-dimensional saddle. Not a literal shape, but a space where lines that start parallel drift apart. Triangles drawn with beams of light have angles that add up to less than 180 degrees. Space expands quickly. Volumes grow faster than you'd expect, and the total size of the universe is infinite. There's no looping, no return path, just more space, extending forever. In an open universe, the expansion behaves differently too. The curvature stretches space in such a way that, over time, distant regions pull apart faster. Galaxies drift farther and farther away. And because of the curvature, light travelling long distances appears slightly different. Shapes stretch, signals weaken, background patterns become subtly distorted. Then there's the flat universe. This one has 0 curvature. Space doesn't bend inward or outward. It follows the familiar rules of Euclidean geometry. Triangles behave the way we expect, 180 degrees. Parallel lines stay parallel. Volumes grow in the way high school geometry says they should. It's the kind of space most people imagine by default, without even thinking about it. But flat doesn't mean simple. A flat universe can still be infinite. It can also be finite, if the topology is right. For example, if it wraps around like a torus, the 3-dimensional version of a donut. The key point is that locally space doesn't curve. The rules are consistent everywhere, and that consistency matches what we observe in the cosmic microwave background and in the way galaxies are distributed. Each of these shapes has consequences for how the universe evolves. In the old models, before dark energy was discovered, the geometry helped predict the universe's fate. A closed universe would expand, slow down, and eventually collapse in on itself. An open universe would expand forever, with the expansion rate slowing but never stopping. A flat universe was on the edge. The expansion would slow down and approach 0, but never quite reach it. That picture has changed. Now we know the expansion is accelerating, driven by something we call dark energy. That means even a closed universe could expand forever if the dark energy is strong enough. Geometry still matters, but it's no longer the only factor. Still, it shapes the behaviour of space. How light moves, how matter clumps, how the early universe formed structure. There are visual differences too, though they're not something you can see directly with your eyes. In a closed universe, the night sky might contain repeating patterns. Light paths might circle back. You might see multiple images of the same galaxy, arriving from different angles after long trips through curved space. In an open universe, those kinds of repetitions wouldn't happen, and in a flat universe the geometry is simple, and the sky reflects that. No unexpected repeats, no strange bending, just structure as far as the eye can see. But detecting those differences is hard. The effects are small, and the distances are enormous. That's why cosmologists look for subtle clues, patterns in the background radiation, correlations between galaxies, distortions in gravitational lensing, tiny deviations that, when measured carefully, tell us which shape best fits the data. So far, the answer is flat. Space appears to follow the rules of Euclidean geometry on large scales. That doesn't prove the universe is flat everywhere, just that the part we can observe behaves that way. Beyond that, we can't yet say. It's possible the universe is globally curved, but that we live in a region that feels flat, like standing in a field on Earth and thinking the planet is flat because the ground under your feet doesn't bend. It's also possible that space is flat everywhere, not because of a coincidence, but because of a process early in the universe's history that smoothed it out. A process we'll talk about soon. For now, the main idea is this. The shape of the universe is more than a visual. It's a set of rules about how space behaves, and those rules affect everything. How far light travels, how gravity pulls, how galaxies form and spread apart. Geometry isn't just an abstract idea, it's a physical part of the cosmos. We can't see the shape of the universe directly. There's no vantage point we can climb to, no cosmic balcony to look out from, but that doesn't stop us from mapping it. In fact, much of what we know about the universe comes from maps, just not the kind made with pens or satellites. These are maps of things we can't touch, shapes we can't walk across, structures too large, too distant, or too faint to draw in the usual way. Still, we build them, bit by bit, with light, with data, with time. The most obvious map is the one we've already talked about, the cosmic microwave background. That faint glow stretched across the sky is more than a remnant of the early universe. It's also a full sky map of temperature variations, tiny, subtle fluctuations, millions of a degree in difference, that trace the early density of matter. And when plotted across the entire sky, those patterns reveal how the universe was structured when it was just a few 100,000 years old. But the CMB isn't the only map we have. As telescopes have improved, astronomers have created deeper, more detailed surveys of galaxies across space and time. Projects like the Sloan Digital Sky Survey and the Dark Energy Survey have collected the positions of millions of galaxies, not just their locations in the sky, but also their distances, determined by how much their light has redshifted as it travelled toward us. That allows scientists to create three-dimensional maps, not just stars on a flat dome, but a full volume of space. When you plot these galaxies, something unexpected appears. Structure. Not a random scatter, but a kind of web. Long filaments, dense clusters, empty voids. This is sometimes called the cosmic web. A vast lace-like structure of matter stretching across the universe. It's not visible in the usual sense. You don't look up and see a glowing net. But it's there, revealed by the positions of galaxies, traced by the paths of light, inferred from the pull of gravity. These structures match what we'd expect from the tiny variations seen in the CMB. The denser regions became galaxies. The emptier regions became voids. Over billions of years, gravity amplified the original differences, pulling matter into filaments and nodes, and by mapping them now, we can see how that process played out. These maps also help us understand dark matter. That's the invisible form of matter that doesn't emit or reflect light, but still has mass. It shapes the universe through gravity, but it's otherwise undetectable. So how do we map something we can't see? The answer is through its influence. Galaxies rotate in ways that suggest more mass than we can account for. Light bends as it passes through regions of space that appear empty, bent by the gravity of something we can't detect. This is gravitational lensing, and when measured across wide areas, it creates another kind of map. A map of mass, not light. A map of where gravity is strongest, even if nothing is visible there. By comparing maps of galaxy positions with maps of gravitational lensing, astronomers can trace where dark matter must be. And over time, those maps have revealed that dark matter isn't evenly spread. It clumps. It forms the scaffolding of the cosmic web. Galaxies form where dark matter is densest, following its invisible threads. There are also maps of expansion, observations of supernovae. Exploding stars used as standard candles allow astronomers to measure how fast different parts of the universe are expanding. These measurements help build a picture of how the expansion has changed over time. Faster in the past, slower for a while, and then faster again, a shift caused by dark energy. These measurements form another kind of map, not of space, but of motion through it, a map of speed, direction, and change. And underneath all of these is a deeper kind of map, one built from equations, from general relativity, from simulations that model how the universe should behave under different conditions. Scientists use these simulations to test how different shapes would affect the structure we observe. They build virtual universes and watch them evolve. Then they compare those virtual maps to the real data, seeing which shape, which contents, and which rules match what we actually observe. These are not guesses. They're built on data, on decades of measurements, on billions of observations. Each new telescope, each new survey adds a few more pixels to the picture. Still, none of these maps are complete. We only see part of the universe, the observable region. Beyond that, the light hasn't reached us. We can't make maps of what we can't detect, so our image of the universe is always partial, always drawn from the inside. But even that partial image tells us something extraordinary. It tells us that space is not smooth, it's not empty, it's structured, textured, and full of hidden layers. It has patterns, motion, memory, geometry. And those features leave imprints on light, on matter, on the signals we detect. So when we talk about mapping the shape of the universe, we're not drawing coastlines or measuring mountain ranges. We're tracking the behavior of light, the motion of galaxies, the distortion of space. And from that, we build a picture of a structure we'll never fully step outside, but which we're learning slowly to read. When people hear that the universe began with the Big Bang, they often imagine something familiar, an explosion, a sudden burst of matter and energy flying outward into empty space, a central point, a loud release, fragments racing in all directions. But that image, while dramatic, isn't quite right. The Big Bang wasn't an explosion in space, it was the rapid expansion of space itself, and that difference changes everything. An explosion happens in a place, it starts from a center, it moves outward, pushing into whatever surrounds it. But in the case of the Big Bang, there was no center, no space already sitting there, waiting to be filled. Space didn't exist yet in the way we understand it. Instead, space itself was stretching. The expansion didn't move through space. It created space. Every region expanded at once, from the inside. Not a fireball flying outward, but the fabric of space growing from within. This is a subtle shift, but an important one. It means there was no edge to fly toward, no outside to burst into. Every point in the universe was part of the expansion. There wasn't a single location where the bang began. Instead, the entire universe, every bit of it, was involved. In those first moments, the universe was hot, dense, and almost incomprehensibly small. Not because it sat inside something else, but because space itself was compressed. Then, suddenly it began to expand, quickly, uniformly. The scale changed, not the contents, and as it expanded, it cooled. Light began to travel, matter began to form, structure began to emerge, but the expansion didn't stop. It still continues, and it's that ongoing expansion, not an explosion that ended, that shapes the structure of the universe today. That distinction also explains why the universe looks the same in every direction. If the Big Bang had been an explosion from a single point, we might expect one side to look different from another, like sparks flying away from a blast. But the universe doesn't look that way. It looks isotropic, the same in all directions, and it looks homogeneous, the same in all locations at large enough scales. That uniformity is exactly what you'd expect from space expanding everywhere at once. Even the redshift we observe in distant galaxies, the stretching of light toward longer wavelengths, isn't a Doppler effect in the usual sense. It's not because galaxies are moving through space like bullets. It's because space itself is stretching between us and them, and that stretch stretches the light, just as it stretches distance and time. This is also why there's no centre of the universe. No spot you can point to and say, that's where it all started. Every location was part of the beginning. Every point has expanded from that early state. If you stand in one galaxy, you see others moving away. But if you stood in a different galaxy, you'd see the same thing. The expansion doesn't have a centre. It has no preferred location. And here's where the idea of inflation enters the picture. Inflation refers to a brief period, a fraction of a second after the Big Bang, when the universe expanded exponentially faster than it does now. Not gradually, but explosively. Not as an explosion through space, but as a sudden ballooning of space itself. This inflationary phase is what smoothed out the universe. It took any initial curvature and flattened it. It took any irregularities and stretched them until they were tiny ripples. It's why the universe today looks so flat, so uniform, so structured. Inflation didn't create the universe, but it reshaped it almost instantly. Imagine blowing up a balloon very rapidly. Any wrinkles or bumps on the surface get smoothed out as it expands. In a similar way, inflation smoothed out the geometry of space. It explains why the observable universe looks flat. Because even if there was some curvature before, inflation stretched it beyond recognition. It also explains why distant regions of the universe look so similar. Regions that should never have had time to exchange information, because light couldn't travel fast enough between them, still appear to have the same temperature, the same density, the same structure. Inflation solves that puzzle by proposing that those regions were once much closer, before being pushed apart by rapid expansion. But inflation is more than just a fix for observational puzzles. It also predicts specific patterns, especially in the cosmic microwave background. Tiny fluctuations, specific distributions of temperature. Those predictions have matched what we observe, which gives the theory strong support. Still, inflation is a model, a framework. There are variations and open questions and deeper mysteries. What triggered it? What caused it to stop? Is our universe just one bubble among many, each inflated from different conditions? These are active areas of research. What matters for now is this. The expansion of the universe isn't a past event. It's a process. It's not a firework that faded. It's a fabric still stretching. Galaxies aren't flying through a cosmic void. They're carried by the stretching of space itself. And that stretching is what gives space its large-scale shape. It's why geometry matters, why curvature becomes visible over time, why light stretches, why structure forms, and why we can say with some confidence that what we see around us began not from an explosion in space, but from the expansion of space. It's natural to think of the universe as a thing with boundaries, a place with an edge, even if we can't see it. We imagine space like a balloon, or a snow globe, or a vast container. So when we hear that the universe is expanding, the next question almost always follows. Expanding into what? The answer, if we're being precise, is that it's not expanding into anything. Space itself is stretching, but not through or over a background. There's no external container, no outside region waiting to be filled. The universe isn't growing like a puddle on a floor. It's not spilling into emptiness. Instead, the very coordinates of space are changing. The scale between points is increasing. The distances between unbound galaxies grow not because they're moving through space, but because space is expanding between them. But that's not easy to picture. So let's come at it from another angle, one we can actually observe. Our view of the universe is limited by time. Light takes time to travel, and the farther away something is, the older the light that reaches us. The most distant light we can see comes from the edge of the observable universe, a kind of horizon, not of space but of time. Beyond that, light hasn't had enough time to get here. It's not that the universe stops, it's just that the signals haven't arrived yet. This creates what we call our observable bubble, the part of the universe we can access with light. It's not a wall or a barrier, it's a limit, shaped by the speed of light and the age of the universe. That limit forms a sphere around us, roughly 46 billion light-years in radius. You might notice that's larger than 13.8 billion, the age of the universe in years. That's because space has expanded during the light's journey. The distance to the source is now much farther than it was when the light began. Everyone in the universe has their own observable bubble. If you were on a galaxy 10 billion light-years away, you'd see a different slice of the universe, centered on you with its own horizon. These bubbles overlap, but they're not the same, which means the universe is larger than the part we can see, possibly much larger, maybe infinite, but we don't know. We only see what's inside our own bubble. Everything beyond that is unobservable, for now and maybe forever. If space continues to expand faster and faster, driven by dark energy, then some regions will never come into view. Their light will never reach us. They'll move beyond the cosmic event horizon, not because they're too far, but because space between us is stretching too quickly for their signals to catch up. This makes the observable universe a bit misleading. It's not the universe, it's just our local window, the part that's sent light to us so far. That window grows as time goes on, but it has limits, and those limits shape how we understand the universe's size, structure, and shape. Still, what we see within that bubble gives us strong clues. The cosmic microwave background wraps around us, forming a full sky map of the early universe. Galaxies are distributed in a statistically uniform way, no preferred direction, no large-scale asymmetry. That suggests that, whatever lies beyond our horizon, it's probably similar, at least in structure. The principle of cosmology assumes that we don't live in a special spot, that the universe looks more or less the same from any large-scale location. But this is still an assumption, a reasonable one, backed by what we see, but not something we can test directly. The regions beyond our bubble may be similar, or they may be very different. They could have different densities, different arrangements, or even different physical constants, depending on the model you choose. That's where things edge into speculation. In some models of inflation, the universe is much larger than our bubble. In others, it's infinite, and in still others, space is broken into patches, each with its own version of physical laws. These are possibilities, not certainties. For now, all we can do is observe our bubble and infer what might lie beyond. The key point is that the observable universe is not the total universe. It's just the part with which we've exchanged light. What we see is shaped by where we are, when we are, and how fast space is expanding. And that's enough to build a rich, detailed model, even if the full story is larger than we'll ever observe. So when people ask what the universe is expanding into, the most honest answer is, that question may not apply. Expansion doesn't require an outside. It's a change in the relationships between things, a shift in scale, not a movement through pre-existing space. And when people ask how big the universe is, the only answer we can be sure of is how big the observable part is. Beyond that, the options remain open, possibly infinite, possibly curved back on itself, possibly extending forever in all directions. So let's say you could go farther, beyond the bubble of the observable universe, beyond the light we've received, past the farthest galaxies we can detect. No spacecraft could get there, no signal could call back, but imagine you had no such limits, just a direction and time. What would happen if you kept going forever? That kind of question feels like a thought experiment, but it's not just a fantasy. It cuts to the heart of what kind of universe we live in, what shape it has, how far it extends, and whether there's such a thing as beyond at all. If the universe is infinite, then the answer is simple in one way and difficult in another. You just keep going, forever. No loops, no boundaries, no edge. Every region of space would be followed by more space, and more, and more. You'd never run out. Even if the distribution of galaxies thinned, space itself would continue. No matter how far you went, there'd always be another region just ahead. Empty or not, it would still be space. But infinity is slippery. It's not a place you reach, it's a condition. If space is truly infinite, that means there is no final point, no ultimate wall. You wouldn't even get farther from the centre because there is no centre. In a universe like that, every point is just as central as any other. Motion becomes relative. You're not travelling to the edge, you're just moving within something that has no total size. Now, if the universe is not infinite, if it's finite but unbounded, the story is different. In that case, if you kept going in one direction, eventually, you'd end up back where you started. Not because you turned around, but because space curves back on itself. The classic analogy is the surface of the Earth. Travel far enough in a straight line, and you circle the globe. The surface is finite, but it has no edge. It loops. A three-dimensional version of that is harder to imagine, but the principle is the same. In a finite, curved universe, continuing in one direction might eventually bring you back. You wouldn't notice the curve directly. Space would seem straight from where you are. But on the larger scales, your path would loop, and the universe would be closed. In both of these cases, infinite or closed, there's no edge. There's no final step, no boundary to hit, no sign that says you've reached the end. That's not how space appears to behave. Whether it loops or stretches endlessly, it doesn't seem to stop. So what if the universe did have an edge? That idea is harder to fit into our current understanding of physics. An edge would imply a place where space stops, where distances no longer continue, where the laws of physics break or change or cease. But everything we've observed suggests space is continuous. Galaxies stretch to the edge of the visible. The cosmic microwave background surrounds us evenly, and models of general relativity don't predict a hard stop. That doesn't mean we've ruled out every possible kind of edge, but it does mean that an edge isn't necessary to explain what we see. The more consistent idea is that the universe is either infinite or finite and curved in a way that wraps around itself. Still, people ask, what if you somehow did reach the end? What would be there? And the honest answer is, we don't have a meaningful picture of what that would be. Space doesn't seem to be embedded in anything. It isn't sitting in a container. If there were an edge, it wouldn't be a wall like in a video game. It would be a place where the concept of space just stops making sense, where coordinates break down, where the structure that defines distances and directions comes to an end. But there's no evidence of such a region, and no need for it in the equations that describe how space behaves. So the question becomes one of curvature and topology. If space is flat and infinite, then you can keep going forever and always find more. If it's curved and closed, then you can keep going forever and eventually return. And if there are higher dimensional structures, if space is connected in strange ways like a three torus, then going straight might eventually bring you back through another direction, or lead to unexpected loops. There's also the possibility that what seems like infinite space is just a repeating pattern. Like a video game background that tiles, you can move in any direction and never see a break, but eventually the same structures appear again. That's called a compact topology. Space is finite, but connected in a way that creates the illusion of endlessness. None of these are proven, but they're possible, they're allowed by the math, and they shape the way we talk about what it would mean to just keep going. It's also worth remembering that space isn't static. As you move forward, the space ahead may be stretching. What you're moving toward may be changing. The light from distant galaxies may never reach you. You might outrun signals from behind and never catch new ones ahead. Your journey would be more than a path through fixed space. It would be a path through changing geometry. So keeping going forever isn't just about distance. It's about moving through a structure that evolves, a shape that's dynamic, a space that isn't fixed in size or form, but stretches, curves, and possibly loops. It's one of the most common assumptions people make when they first think about the universe, that somewhere out there, maybe far away, there must be a centre, a place everything started from, a central point of origin, like the centre of a firework or the spot where a stone splashes into a pond. But the universe doesn't work like that. There is no centre, not just because we haven't found it, not because it's too far away, but because the very idea of a centre doesn't apply to the kind of space we live in. If you look at galaxies around us, you'll see they're all moving away. That might make it feel like we're in the centre, with everything flying outward. But the same observation would be made from anywhere else. Pick a galaxy 1 billion light years away. From that point, the others would also seem to be receding. The expansion is uniform. It's happening everywhere, not from one location. This is what it means for the universe to be homogeneous and isotropic, the same in all places and the same in all directions at large scales. That symmetry is what erases the concept of a centre. It's not that we're at the middle, it's that there is no middle. When space expands, it does so uniformly. Think of the surface of a balloon as it inflates. The rubber stretches equally in all directions. Any point on the surface will see the others moving away. But the surface itself has no special location, no centre on the two-dimensional surface. The centre of the expansion is not on the balloon. It's in a higher dimension we're not part of in that analogy. Now translate that idea to three-dimensional space. The universe expands like that balloon surface, but in every direction, with no preferred spot. This applies whether space is flat, open, or closed. In each case, the expansion doesn't begin from one location. It begins from a state, a condition, a moment in time, not a place in space. The Big Bang wasn't the birth of a dot that exploded outward. It was the emergence of space everywhere at once, and if space is infinite, then that moment happened at every point, with no beginning point to point back to. Even in a finite universe, one that wraps around itself, there's still no centre. The curvature may be different, the topology may loop, but no single place serves as the origin of it all. This is a big shift from how we're used to thinking. In everyday life, most things have a centre. Rooms, cities, objects. Our mental models are built around points of reference. Something is always in the middle. But in cosmology, that breaks down. There's no central location from which the universe is expanding. There's only relative motion, only distances changing. The centre we sometimes imagine is a leftover from those mental models, from watching explosions or looking at diagrams with arrows pointing outward. But those diagrams are simplifications. They help show direction, not structure. In the real universe, no matter where you go, you can think of yourself as stationary, as if everything else is moving away. And in a way, that's true, because the expansion isn't pushing galaxies through space. It's increasing the space between them. There's another way to think about this. If the universe did have a centre, there would be signs, anisotropies, a preferred direction, patterns that change depending on where you look. But we don't see that. The cosmic microwave background is smooth. The distribution of galaxies, when averaged over large distances, is uniform. There's no gradient that points to a special location. And that supports the idea that no centre exists. Even in the early universe, when matter was more evenly spread and structures hadn't yet formed, there was no centre. The density was high everywhere. Light couldn't travel far, but even then space was expanding equally in all places. Some models propose universes with complicated topologies, twisted, wrapped, or repeating. In those, direction can be confusing and space can fold back on itself. But even then, a centre doesn't appear. These aren't shapes that revolve around a single core. They're shapes without focal points, structures built on relations, not positions. And this matters for how we ask questions. If you're looking for where the Big Bang happened, the answer is everywhere. If you're asking what direction to head in to find the origin, there isn't one. You're already standing in it. The Big Bang didn't happen in a part of space. It happened to space itself. The absence of a centre also helps explain why the universe looks the same in every direction. Why we don't see a lopsided sky. Why cosmic background radiation is nearly uniform. Why no matter where you point a telescope, the large-scale picture is similar. and that ties back to geometry. The shape of the universe, whether flat or curved, can be described without needing to point to a middle. Shapes in general relativity are defined by how distances behave, not by what's in the middle of them. Curved or not, space works by internal rules, not by reference to an external point. For a long time, scientists thought the universe's shape might also be its destiny, that the geometry of space could tell us how the universe would end, or whether it would end at all. A closed universe, curved like a sphere, would eventually collapse back on itself. An open universe, curved like a saddle, would expand forever. And a flat universe would balance between the two, slowing its expansion, but never quite stopping. That idea made sense for a while. Geometry and fate were tied together, two parts of the same story. Measure one, and you'd know the other. But that story changed in the late 1990s. Astronomers were measuring distant supernovae, bright, exploding stars that serve as standard candles. By comparing how bright they appeared to how far away they were, scientists could estimate how fast the universe had been expanding over time. The expectation was that the expansion would be slowing down, pulled back by the gravity of all the matter in the universe. But it wasn't. What they found instead was something surprising. The expansion was speeding up. Distant galaxies weren't just drifting away, they were accelerating. The space between them wasn't just growing, it was growing faster and faster. Something was pushing it outward. That something was named dark energy, a placeholder name for whatever force or field or property of space was causing this acceleration. And it turned out that dark energy didn't just affect the expansion, it changed the relationship between geometry and fate. Before dark energy, a closed universe was expected to end in a big crunch, expansion, slowing, reversing, and collapsing into a dense point. An open or flat universe would expand forever, with the rate depending on the shape, but with dark energy, that link broke. Even a closed universe could expand forever if dark energy kept pushing. The shape still mattered, but it wasn't the deciding factor anymore. So what is dark energy? We don't know exactly. It's not a form of matter. It's not something we can see or touch. But it makes up about 68% of the energy content of the universe. The rest is mostly dark matter and a small fraction of normal matter, the stuff we're made of. That means most of what drives the behavior of the cosmos isn't visible. It's silent, spread out, built into the structure of space itself. One possibility is that dark energy is a property of empty space, a constant energy density that doesn't dilute as space expands. That would explain why the expansion doesn't slow down. As space grows, there's more room for dark energy to act, and its push stays steady. Another possibility is that dark energy is something more dynamic, a field that changes over time. In those models, the future of the universe depends on how that field behaves. Will it remain stable? Will it grow stronger? Could it decay into something else? Each version leads to a different kind of future. If dark energy stays constant, a cosmological constant, then the universe will keep expanding forever at an accelerating rate. Galaxies will drift apart until they're no longer visible. Stars will die out. Matter will grow cold and dark. Eventually, the universe will be vast and nearly empty. A slow fade into silence. This scenario is sometimes called the Big Freeze. If dark energy gets stronger over time, the expansion will accelerate even faster. Not just galaxies drifting apart, but galaxies themselves pulled apart. Then stars, then planets, then atoms. Space would expand so rapidly that all structures would be torn apart. This is called the Big Rip. It's a more extreme end, and one that depends on dark energy behaving in a very specific way, which current data doesn't favour, but hasn't ruled out entirely. If dark energy fades away or reverses, the universe could still collapse. Expansion could slow, then stop, then contract. That would bring back the possibility of a big crunch, everything falling back together. But again, observations suggest dark energy is stable, or nearly so. So where does that leave geometry? It still plays a role. A universe with positive curvature might be finite. One with negative curvature might be infinite. A flat universe might sit at the boundary. But fate no longer follows shape the way we once thought. The deciding factor now is energy, especially dark energy, and how it behaves across time. Still, the discovery of accelerating expansion didn't erase the importance of shape. It changed how we understand it. It showed that the structure of space isn't just passive, it evolves, it reacts, it stretches in ways we didn't predict. And that stretch tells us not just about where we are, but where we're going. Observations continue. Telescopes now measure the clustering of galaxies, the spread of supernovae, the bending of light, all to refine our picture of dark energy. It's one of the biggest open questions in physics. What is this force that shapes the largest structures in existence, and yet leaves no visible trace? In the meantime, we live in a universe where expansion doesn't slow, where the fabric of space grows quietly, without edges, without a centre, shaped not just by mass, but by something even deeper. And that quiet push defines the long-term path of everything. For a long time, it seemed like we had the shape figured out. Not in fine detail, not down to the edge, but close enough to build a working picture. The universe looked flat. The cosmic microwave background matched the predictions of flat geometry. Large-scale surveys of galaxies showed no signs of bending or wrapping. The models that fit our data best all pointed in the same direction. Space was flat, or nearly so, and maybe it is. But the closer we look, the more we realise that certainty comes with limits, not because the measurements are wrong, but because they can only reach so far. The universe we see is a sample, a bubble of observation, and even within that bubble, the signals are faint and the structures are complex. What we call flat could still be slightly curved, just beyond our ability to detect it. This isn't just a theoretical worry. Even small changes in curvature can affect how we interpret what we see. If the universe is slightly closed, a little curved inward, it might loop back on itself in a way we've missed. If it's slightly open, curved outward just enough, the expansion might behave differently at scales we haven't yet measured. These shifts wouldn't be obvious from our spot in the universe. We'd see them only in the edges of the background radiation, or in the slow drift of galaxies billions of light years away. In 2019, a paper analysing data from the Planck satellite hinted at a small but unexpected signal, a possible preference for positive curvature. It wasn't strong enough to overturn the flat model, and later studies suggested it might be a statistical fluke. But it was a reminder. The shape we think we know is still a conclusion drawn from models, assumptions, and boundaries. Those models are good. They're consistent. They've passed a long series of tests, but they're still maps, not territory. They take what we observe and fill in the rest. And sometimes they rely on simplicity, the assumption that space is smooth, uniform, and cleanly curved. But the universe is messy, matter clumps, voids stretch out, gravity tugs in complex ways, and even small irregularities can throw off a shape measurement if not accounted for. There's also the deeper question of topology, not just the curvature of space, but its structure. A universe can be flat and still finite, if it loops around in just the right way, like a three-dimensional version of a video game world that wraps around on itself. If space does that, the curvature might be flat, but the shape is still closed. It wouldn't look infinite even though it had no edge. We haven't seen direct evidence of that kind of structure, no repeating patterns in the sky, no mirrored galaxies. But again, that doesn't mean it isn't there. It just means we haven't found it yet, or that it lies beyond our observable reach. The more precise our instruments get, the more we learn to question even our best guesses. That's not a failure, It's a sign of progress, a reminder that models are tools, not truths, that the shape we thought we knew is the shape our data could resolve, not necessarily the shape that is, and that uncertainty is part of science. We don't look at the universe and declare its shape. We measure it, model it, test it, and revise. If we find a slight curve where we thought there was none, we adjust. If we see patterns where we expected randomness, we ask why. That's how our picture sharpens, not by reaching a final answer, but by improving the questions. So far, the best fit is flat. The distances and angles match. The fluctuations in the microwave background align with a universe that doesn't curve, at least on the scales we can see. That's why most models use flat space as a starting point. It works, it predicts, it holds. But if space does have a slight curve, inward or outward, we'll only know by pushing the edges of what we can observe, by refining our surveys, by studying deeper parts of the sky and tracking light with more precision. And even then, we'll never see it all. There will always be a horizon, a boundary set by light and time. That's what makes cosmology different from other kinds of science. We can't run experiments on the universe. We can't step outside it and look down. Everything we know is measured from inside, using particles, radiation, and geometry to piece together a shape we can't fully touch. And yet, we've mapped billions of years of expansion. We've measured the faintest patterns in ancient light. We've built models that predict the behavior of matter across unimaginable distances, all with just the signals that have reached us, inside a finite window. The shape we thought we knew may still be the right one. But even if it changes, even if it shifts slightly with new data, that won't undo the progress we've made. It will just bring the picture into better focus. It's easy to think of the universe's shape as fixed, like the shape of a table or a mountain or a crystal, something permanent, once set, always the same. But space isn't solid. It isn't frozen. It bends under gravity. It stretches as the universe expands, and over time it changes, not always dramatically, not always in ways we can feel, but in ways that shape the evolution of everything inside it. So yes, the shape of the universe could be changing. In some ways, it already has. In the early moments after the Big Bang, space was extremely curved. The energy density was high, matter and radiation were tightly packed. At those scales, gravity was intense and geometry was dynamic. But in that brief and violent phase, what we now call inflation, something changed. Space expanded exponentially, and with it, any initial curvature was stretched out. That process smoothed the geometry, flattened it. Not into perfect flatness necessarily, but close enough that the universe today appears remarkably flat across vast distances. That change wasn't cosmetic. It restructured space. The curvature that may have once been significant became imperceptible, diluted across an enormous volume. So that's one kind of shape change, curvature being flattened by rapid expansion. Another kind of change is happening even now. As the universe expands, its overall density decreases. That affects the balance between matter, radiation, and dark energy. In the early universe, radiation dominated. Light was everywhere, dense and hot. Then matter took over, forming stars and galaxies. More recently, dark energy became the dominant force. Each phase affects how space evolves, not just in speed, but in shape. Dark energy in particular changes the story. Its presence accelerates expansion, and that acceleration affects curvature. It doesn't erase it, but it makes it harder to detect. In a universe where expansion accelerates forever, even a slightly curved geometry can become indistinguishable from flatness over time. The fabric stretches so quickly that local distortions vanish in the distance. So in that sense, the shape of the universe doesn't just change, it becomes harder to define. Geometry gets smoothed by scale, curvature fades into the background. The longer expansion continues, the more subtle the shape becomes. there are other ways shape might change too, ones we haven't confirmed, but which some theories allow. In quantum cosmology, the early universe wasn't just expanding, it was fluctuating. Quantum fields rippled and tunneled. Space itself may have undergone transitions, from one shape to another, from one set of rules to another. These aren't changes we can observe directly, but they're part of models that attempt to describe the very beginning. Some versions of inflation even propose that different regions of the universe may have inflated differently, forming separate pockets, or bubbles, each with its own geometry. In that case, the shape of space wouldn't just change over time, but vary from place to place. Our universe might be one domain in a larger multiverse, where geometry is local, not global, where shape isn't a universal property, but a regional condition. In more speculative theories, ones involving higher dimensions or string theory, the shape of space might depend on hidden structures, tiny, curled-up dimensions too small to see directly. If those hidden shapes shift, the geometry of our visible universe could change too, not necessarily in obvious ways, but subtly, through the behavior of particles or the direction of expansion, or the distribution of energy. Even the topology of space, its large-scale connectivity, could evolve. If space is looped or knotted in some way, extreme events might alter that structure, not in any scenario we expect soon, but in the deep future or in the conditions of the early universe, topology might not be fixed. But in the models that describe what we see now, the shape of space is largely stable. It's not rigid, but it's not wildly fluctuating either. It responds to changes in energy. It evolves with the contents of the universe. It bends under gravity, smooths under expansion, and drifts towards simpler forms as time goes on. Still, even if curvature remains subtle, even if topology stays hidden, the idea that the universe's shape can change reminds us that space is active. It's not just a container, it's a participant. It stretches, it bends, it evolves, it carries the imprint of past transitions, and it sets the stage for future ones. So when we look up and ask what shape the universe is, we're really asking, what is the geometry right now? What was it in the past? And what might it become? Because shape in cosmology isn't a single answer, it's a history. So after all of this, the light, the expansion, the curvature, the maps, the limits, comes a simple question that floats quietly above the rest. If the universe has a shape, then what? What does it mean to live inside a space that curves or stretches, that might be infinite or might loop around itself? What does it mean to float through a geometry we can never step outside of, that defines every direction, every movement, every possible distance we can measure? Some answers are technical. A shape determines how light travels, how gravity acts, how large-scale structures evolve. It sets the stage for what kinds of things are possible, how galaxies form, how time behaves, how the past connects to the future. If space curves too much, it might collapse. If it's too open, it might thin too fast. If it's flat, it might balance just right for life to arise, stars to burn, atoms to bind. But beyond the equations, the measurements, the telescopes, the data, what does it mean? It means we live in something, not something like a house, or a room, or a sky, but something that has structure, that stretches beyond us, that isn't flat by default, but shaped by history, energy, and motion. The universe we inhabit is not an abstract void. It's a fabric. It has rules. It has a shape, and that shape is real. And if it has a shape, then maybe it also has a context. Because as soon as you start describing space as our universe, you have to wonder, could there be others? Not metaphorically, but physically. Regions where inflation went differently, where the geometry bent the other way, where particles followed other rules, or where time flowed along another curve. If space can stretch, maybe it can branch. If the universe has a shape, maybe it's just one fold in something larger. These aren't idle questions. They come from theories that try to unify what we know. Inflation, string theory, quantum gravity, all of them allow or even suggest the existence of multiple domains, separate spaces, different shapes, a multiverse, not of fantasy, but of mathematical possibility. That doesn't mean we'll see them. They might be forever cut off, beyond causal contact, beyond our light cone, beyond any future we can reach. But the math points outward, not toward an answer, but toward a wider landscape. And if that's true, if space is just one patch among many, then the shape of our universe becomes something else entirely, a condition, a setting, a local chapter in a story without edges. We might be in a universe that's flat, infinite, and expanding forever, or one that's gently curved, looping quietly behind the scenes, or one of many, each stitched together by forces we can only model in theory, each shaped by the same laws, or by entirely different ones. None of that changes what we are. None of it makes this place less real. If anything, it makes it more extraordinary. Because in all the possible ways space could be shaped, bent, folded, looped, sliced or torn, we're in one where galaxies formed, where stars shine, where light travels and time flows, where something can ask, what is the shape of everything? And try to answer. That's what the shape tells us, not just where we are, but what kind of space allows questions like this to exist. What kind of structure can carry life and thought and curiosity? So if the universe has a shape, then what? Then it means we're part of something structured, something evolving, something vast, something worth exploring, one quiet question at a time. Until next time, breathe slowly and remember, the universe is more than where we stand. It's the space between us, the threads of light we share and the shape of our thoughts as they wander across the stars. Good night and sweet dreams.